just to recall the things that I want to show today. So we have the Hitchin system, the Hitchin Simpson theorem, which says that given a polystable Higgs bundle, E phi on X, so here X is a compact Kaehler manifold. There exists a metric on E such that when I take lambda, square root of minus 1 lambda of FA plus phi phi star, this is some constant times the identity. And this lambda is contraction with the Kaehler form. So this is a Hermitian endomorphism. And the statement is that that's just a constant multiple of the identity. And so that's the theorem that I want to, for which I want to outline the proof on Wednesday. And then under an additional assumption, and I think I got this wrong yesterday, so I apologize for that. Let me correct what I said. I think I said something wrong. If I make the additional assumption that the first Chern class, or let me write that as Chern 1, intersected with with the Kaehler form is 0, and Chern 2, not C2, but Chern 2 is 0. If I have these extra conditions, topological conditions on the bundle, then that implies that in fact this lifts, and so mu is 0, and this actually lifts, and this is 0. In that case, that implies that the connection gotten by adding this Hermitian piece to the unitary connection, the Chern connection for this metric, this guy is flat. Okay, so that's the direction going from the Hitchin-Simpson theorem to flat connections. Okay. And conversely, what I'm going to talk about today is the Corlett theorem, which goes the opposite direction. So conversely, given a flat connection, and so here, this guy is polystable, and so this connection here is semi-simple. So given a semi-simple, representation or flat connection, then there exists a metric such that when I write nabla as b plus psi, so this is simply the Hermitian piece of the connection, and this is the unitary piece of the connection, which I can do whenever I have a metric, and I let phi be the 0, 1 part, then the d-bar operator A is integrable. It defines a holomorphic bundle. D-bar A of phi is 0, and so this is a holomorphic section, and phi is 0. So i.e., this connection comes from a Higgs bundle over here. So this is the correspondence. This is the non-abelian knowledge correspondence. So let me give some applications of this, because last time I wanted to mention applications and I didn't have time. So let me just list a few. There are many, of course, and so I'm just going to list very, very few applications, but just to give you an idea that this is actually a useful kind of picture. So first of all, there's a very famous topological kind of condition on stable Higgs bundles that comes out of this, and that's the Bogomolov inequality. So if E is stable, again on a compact Kaehler manifold, then we get an inequality of Chern numbers. So C2, 2R, C2 of E minus R minus 1, C1 squared of E is positive. So here I realized that I was using the same letter, I think, for the dimension of the manifold and the rank of the bundle. And so from now on, R is the rank of the bundle, and N is the dimension. Okay, so this is a sort of topological restriction that comes out of stable Higgs bundles. Another application is a little bit deeper in terms of the actual structure of this correspondence. So the statement is actually a little bit stronger. It really says that the deformation, so here, the way I stated it last time is that M Betty is homeomorphic to M Higgs. And actually, the statement is a little bit stronger. It says that the deformation complexes essentially are isomorphic. Quasi-isomorphic. And so in other words, the deformation complex for a flat connection as a local system, I can write down the deformation complex for that moduli problem, and I can also write the deformation complex for the Higgs bundle moduli problem. And at a semi-stable, semi-simple flat connection, then these complexes are isomorphism essentially from this correspondence. And combined with a theorem of Goldman and Milson, this implies, and this was noted by Simpson, that at a semi-simple point, M Betty is quadratic. Which means that the singularities are essentially, the tangent cone is essentially a quadratic cone. And this follows from Goldman-Milson's work. Okay, so this also has applications, in other words, to the structure of the singular set on the Betty moduli space. Another application to Kaehler groups is the following. So here, the flat connection, as I've said, is essentially the same thing as giving a representation of pi 1 of x into the isometry group of a symmetric space. So in this case, the way I've written it is in the SLN case. Okay, but one can generalize this picture, and the fact that we have a relationship between the flat connection and Higgs bundles leads to some restrictions on the possible fundamental groups of Kaehler manifolds. So there are many theorems in this direction. Let me just state a couple that come. So this really comes directly from this correspondence. So these are due to Simpson. So here's a precise statement: is that if gamma is a lattice in a simple Lie group, and gamma is a Kaehler group, is the fundamental group of a compact Kaehler manifold, then that implies that G has a compact Cartan subgroup. So this eliminates many lattices from being possible fundamental groups of compact Kaehler manifolds. So this condition eliminates lattices in complex Lie groups and, for example, SLNZ, n bigger than 3, etc. Okay, so there are many possibilities that come from this. There's another application that really comes from the harmonic map theory, not so much the Higgs bundle kind of picture, but from this Corlett idea, and this is due to Carlson Toledo. And this says that a Kaehler group cannot be a lattice in a hyperbolic space. So it cannot be a lattice in SON1 for n bigger than 3. So using some same ideas. Yes. This one, yeah. I don't know the answer to that question, but it may very well be the case. It's definitely a diffeomorphism of smooth locus, exactly, yeah. Yes. Okay, so anyway, so here are some applications. I just wanted to state those. And I'll state some more actually later on when I talk about harmonic maps to R trees as well. So there are some interesting applications there. Okay. So today what I wanted to do, hopefully I have time for this, is to prove the Corlett theorem. So let me just start on that. So again, really the Corlett theorem is much more general. It has to do with the existence of harmonic maps from any Riemannian manifold. And then in the case where X is compact Kaehler, then we have the Sue-Sampson result on pluriharmonicity, and that's what gives the correspondence with Higgs bundles. So let me start out with the Corlett theorem. So again, let me just restate it here. So suppose X is just a compact Riemannian manifold. Rho into SLNC is semi-simple. Let me phrase it in terms of an if and only if. So rho is a representation of SLNC, then rho is semi-simple. So by this I just mean a direct sum of irreducible representations. It's semi-simple if and only if there exists a rho equivariant harmonic map from the universal cover to n, which is this X tilde, yes, thank you. So this is an equivariant map, meaning that if I take U of gamma X, this is rho of gamma of U of X. Okay? That's what I mean by it. And gamma is in the fundamental. Okay, so let me set up this problem and give you an idea of the proof. So first of all, I'm going to state some things that are fairly straightforward. We can go into more details if you like. So here, let me just, for convenience, call, I don't know, V is going to be my Cn with the natural action of SLNC on it. And so then I'm going to take a realization of N in terms of Hermitian matrices. So these are just N by N matrices that are Hermitian and determinant 1. Okay? And then the action of SLNC on a point H is just GH G star. Okay, so it gives a concrete realization of what this action is in a symmetric space. Okay, so let me state some facts, first of all, that might be useful to keep in mind. So here, an equivariant map is equivalent to a choice of Hermitian metric. On the smooth bundle on X. So this symmetric space is the space of all Hermitian inner products on Cn. And the Hermitian metric on X is simply a family of Hermitian inner products. So this is fairly straightforward. Moreover, if I have a flat connection, we get an equivariant map. By parallel translation. So this really only depends on one thing, namely a choice of the base point. Okay. So if I'm saying anything confusing, stop me and I can go into more details. But basically what I'm saying here is that I've got a flat connection on the trivial bundle up here by pulling back my flat connection on X. And now I choose a base point, and I just do parallel translation of a choice of frame at that base point, and I take the inner product with respect to that standard inner product at some point. That gives me a Hermitian metric, and that's what gives me a point. So I start out, so here I have it's the trivial bundle. It's the trivial bundle. So if you like, just take e to be the trivial bundle. So I'm thinking of this as being equivalent to a flat connection on a smooth vector bundle on X, which we may as well assume is the trivial bundle. Okay. A third statement here is that given a Hermitian metric and a connection, any connection, any SLNC connection, I can always, and a connection lambda, delta, I can always write this as I've been saying, a unitary part and a Hermitian part. So psi is a one form, and dA is a unitary connection. So this is also pretty clear. And so now here's kind of the key thing is that, so if I have a metric, yeah, so the energy so with respect to this decomposition here, the energy of the associated equivariant harmonic map is twice the normal sum. Okay. So this requires just a little bit of calculation, but using the fact that this is unitary. Okay, and so this is actually the link here. So this is, by the way, the link between the harmonicity of the map U and this condition BA star of size zero. That's essentially coming from this equivalence that we have. Okay, so these are some facts that, as I say, are not too complicated to work out. And let me just assume those, if I can, and go from there. Okay, so as I say, once we find an equivariant harmonic map, then that gives us a Hermitian metric on E. And so that's why in the literature, this is sometimes called harmonic metric. 1 and 2. So first, so 1 doesn't involve a flat connection. So I have an equivariant map that's equivalent to a Hermitian metric on the bundle. There's no connection there. The point is that if I have a flat connection, then there's a natural way to get an equivariant map by parallel translation. I mean, right. So what I'm going to do, maybe I should say this differently. So pi 1 on n, that's through the representation, right? So I'm fixing a flat connection or a representation, and so I'm acting on n via this representation. That's right. The flat connection is the holonomy of this flat connection is rho. So given a representation, I think of this as a flat connection. Okay. So let me just be a little bit more explicit here. So what do? I take a frame from my vector bundle, add a base point, and that's tilde. And now I do parallel translation. And I can do this globally. Because it's X tilde is simply connected. I have a flat connection. I have a global parallel frame. Okay. So now, at a given point, I can take the inner product of these two with respect to the trivial. I've got the trivial bundle, it's a fixed or Hermitian metric there. Standard Hermitian metric on Cn. I can take this inner product with respect to that metric at a point P, not P, at a point X, the universal cover. This is some Hermitian matrix, and if the connection is an SLNC connection, then that's determinant 1, and so that's my point in N. So I define this Hermitian matrix to be U of X. And it's equivariant precisely because of this statement. So moving the map around by an action of SLNC is the same thing as conjugating the connection by that associated gauge transformation. So let me just clarify that again. So if given a map from X into SLNC, G and an equivariant map here, N, let's say rho equivariant, okay, then I can simply pointwise multiply this map by G. So I lift this map up to X tilde, I pointwise multiply this guy. And what is this? This is another map which is equivariant for G nabla G inverse, or maybe the other way around. So moving the connection in a complex gauge orbit is the same thing as moving this map around. That's the point of these two statements, putting them together like that. Okay. All right. So that takes some time to do these two. So now let me state the two key limits. So here we want to prove both directions, and so what I'd like to do first is show why semi-simplicity is important. Right? Why is the existence of an equivariant harmonic map require this condition? Okay? So suppose that there is an equivariant harmonic map. Sorry, got the wrong piece of paper here. Suppose I have an equivariant harmonic map. And harmonic, then that implies that nabla is semi-simple. Okay. So let me actually do this proof. Okay, so again, whenever I write rho and nabla in the same line, I'm thinking of rho as being the holonomial of that flat connection. Okay? So suppose not, right? So suppose that there's an invariant subspace, Cn, so preserved by nabla. So this is, so here I'm thinking of V as being the, I guess I wrote it as E over here. V is the flat bundle with the flat connection. So suppose it's not semi-simple, so I have a sub-bundle that's preserved by the connection. That's right. It implies rho is semi-simple. I'm going to confuse those two issues. Right? The flat connection semi-simple if there's no invariant subbundle. And that's the same thing as saying that the monodromy is semi-simple. So suppose that there is an invariant subbundle, so preserved by nabla. Then that means that I can write my connection as in terms of some second fundamental form here. It's an SLNC representation. Yeah, semi-simple means that I can split this down. Exactly. That's what I'm trying to show. So I want to show that beta is 0. Exactly. So beta is a 1 form in Hom of the quotient. Let's say that V2 is the quotient. V2 here, I've got a metric floating around. So V2 is V1 perp. Okay, so this is Hom of V2 perp V1. And simplicity means that I can, by induction, beta is 0. So I want to show that beta is 0 here. I want to show that the connection splits. Okay. So how do you do that? You do this by a gauge transformation. So a little calculation first. I want to calculate what psi is. And what it is where here I've written nabla 1 as BA1, psi 1, etc., with respect to the induced metric. Okay. So this is the structure of psi. And so now I want to do a gauge transformation. And here is the one that I want to do. So I deform the metric. So I'm using H now for my metric. And here I want to take this as minus T times the rank of V2 times H1. So I do this in such a way that the determinant of this metric is still 1. All right. And this is a geodesic homotopy in the space of metrics. In N, in the space of metrics. So by just scaling this in this way, this is a geodesic with respect to the invariant metric on N. Okay? And so now you want to calculate the energy, and the way you calculate the energy is by using this, this formula that I wrote here. So what is the energy? Let me just fit it right here, and I can finish. So the energy of this new map is this. So it's 1/4, and then the norm psi 1 plus the norm psi 2, and then plus the norm of the second fundamental form. T over 2 times the rank of B. Okay. So, right, so I can either think of this as scaling the metric in this way or doing a gauge transformation of the flat connection and then taking the associated map that comes from the statement in 2. That absolutely perfect. Okay? So now I just calculate the energy of that map by doing this, and we arrive at this. Okay? So here, this UT, as I said, is a geodesic homotopy. Okay? So I need one little extra theorem, and that's the theorem of Hartmann, which really goes back to the Eel-Sampson kind of point of view, is that when N has non-positive curvature, the energy is convex on geodesic homotopy. Okay, so again, if I take maps to any non-positively curved metric space, I take two maps and I look at the geodesic homotopy between them, then the energy along that path of maps is convex. That's the statement. Okay, so that is essentially a consequence. It's completely a consequence of the non-positive curvature of the color. Okay? So the energy is convex along geodesic homotopies, but look at this. Here's the energy on this geodesic homotopy, and it's bounded as t goes to infinity, for example. Okay? So the only way that it can have a critical point at t equals 0, so we said that U0, the original one, was a harmonic map, right? So the only way this can have a critical point at U0 and be bounded as I go to infinity and be convex is if it's constant. Right? So this implies, sorry, running out of room here. This implies that E is constant. Which implies that beta is 0. Okay, so that's the okay, so maybe a little bit too much to try to pack in there, but it's once one unpacks the definitions here, it's really just a consequence of hardness. Okay, so that's the necessity, the semi-simplicity, and so now, sorry, I'm just getting a little bit lost here. So now let me do the actual. So the second key lemma is the following. So suppose that Uj is a sequence of row equivariant maps. Row equivariant maps on X, and here rho I'm going to assume is irreducible. Okay, by semi-simplicity, it suffices to prove now the existence part for irreducible representation. I already know that semi-simplicity is built in, so I'm only going to do this for irreducible representation. So suppose that rho is irreducible, and I have a sequence of equivariant maps with a uniform Lipschitz constant. Okay, so this is going to be the key operating factor. Then for any point P, the set UJP is bounded. So let me give you the picture. So the picture is that you have your symmetric space like this, and now you've got the row equivariant maps. Now suppose that somehow I could, and I've got a uniform Lipschitz bound on this. So I can take, for example, like generators for the fundamental group, and look at the image of the generators. So I've got the image of that equivariant map by a fundamental domain in the domain. Okay, and so this is my for each j I've got this image, and the question is can you push this somehow off to infinity? Well, you've got a uniform Lipschitz bound, so the diameter of this set is uniformly bounded as I go out to infinity. Okay? Now, how can that happen in an NPC space? The only way that can happen is if you're fixing a point in infinity. Okay? So the conclusion here is that there must be a point in the boundary at infinity of the NPC space. That's the intuition of this picture. But if you have a fixed point at infinity, then that means that the representation must have been reducible. Okay, so ruling out the existence of fixed points at infinity, morally speaking, should be enough to make sure that these maps do not diverge. So that's the intuition. Let me try to give a little bit more rigorous proof of that statement. Not sure if I should actually do this. Yeah, so let me prove this rigorously. So let's let Hj be UJP, and then I choose. So again, I suppose not. So suppose that this is unbounded in the space of Hermitian metrics, then the Hermitian metrics are going off to infinity, so I can rescale them. To converge to an endomorphism, which is not zero. Okay? And since the determinant of Hj is always fixed to be 1, that implies that the determinant of H infinity is 0. And that implies that there's some non-trivial term. It's not 0, and it's not D. Okay? I guess I'm using V for Cn now, so sorry. Okay, so now let G be rho of some gamma. Okay? So I know that I've got a uniform Lipschitz constant. Okay, so whatever that means exactly, it means that the metrics are bounded from each other. So that means when I use when I look at the metric associated to Hj and associated to some fixed G times Hj, these remain a bounded distance apart by the Lipschitz bound for the equivariant maps. So this difference here is bounded. Now, what does that actually mean? So how do I write the metric in terms of this? This is the standard metric conjugated by G. This is the standard metric inserting H, and this is bounded maybe by some other constant. All right, well now multiply by epsilon j, and let j go to infinity. So the right-hand side goes to 0, and over here I get convergence. So that implies that, actually this goes to 0 here, so that implies that G, H infinity, G star, V, W is equal to H infinity, V, W. And so now if I take V to be in the kernel of H infinity, so this is 0, V is in the kernel. This is H infinity G star, V, G, W. And W here is completely arbitrary. Okay? So that implies that this G, or rather G star in this case, actually fixes V. It is also in the kernel. So that implies that the representation fixes. So that's the proof of this lemma. So if the representation is actually irreducible, this can't happen, and so we get a calculation. I can always choose the epsilon so that it converges to something non-zero. So epsilon is like 1 over the largest eigenvalue or something like that of that matrix. So I just choose it so. Choose it not too small, exactly. Okay, so the reason I go through this is because we'll see that this is also very similar to what happens in the proof of the Hitchin-Simpson theorem as well. It's the same idea of this rescaling of metrics to arrive at some non-trivial endomorphism. And the structure of that endomorphism gives you a computation. Okay, so this lemma essentially finishes the proof. Let me just say a few words. Here I won't go into more detail now, but the point is that we can always arrange for a sequence of maps that works well. So given rho, so we can find a sequence uj of rho equivariant maps with the following properties. One is that the uj is energy minimizing. Okay, so this the limit of uj is equal to the lim in over all rho equivariant maps. So it's an energy minimizing sequence, and the uj have a uniform Lipschitz bound. And then one other little technical condition is that I want so let me just write down this technical condition, is that the tension field, which is by definition d gamma star d uj, goes to 0 in L2. Okay, so this is a rather technical condition, but we can arrange for a sequence of maps that satisfy these conditions, and so what does that mean? That means that so the uniform Lipschitz bound plus this second lemma that I wrote down here, the fact that we know that the image of the maps don't go off to infinity at one point, say, means that we can use the Ascoli's theorem. So imply by Ascoli's theorem that there is a convergence subsequent. Okay, and so under these other assumptions, you can then prove that convergence subsequence actually converges to a harmonic. Oh, this is just notation. This is sometimes called the tension field, but it's just the condition for a map to be harmonic is that this is 0. So we'd like that to be going to 0 in some very weak sense. And sorry? It's 0 for energy minimizing, so we'd like to make sure that along our sequence, right. So it looks like, you see, I mean, you're right. It looks like these two are almost equivalent, but just to say that it's energy minimizing, you want a little bit more, right? You want the energy density to be going to 0 now. See, the energy is the L2 normal backup. And I really want this tension field to be going to 0 now. Okay, so, so the way that you construct this sequence is by choosing an arbitrary energy minimizing sequence and then improving it to satisfy these things, these extra conditions, by using the harmonic map flow. This is one way to do it. So harmonic map flow, I won't go into too many details here, but the harmonic map flow is the gradient flow for this tension field. And so if I had on a compact manifold, this is how Eons and Simpson actually prove the existence of a harmonic map. And so here I'm just doing it slightly different than the equivariant case. But in any case, you can satisfy these conditions by taking an arbitrary energy minimizing sequence and then just improving it a little bit by doing the flow for a certain amount of time. Okay, so so I think that's about all I want to say about the structure of the features. Okay, so right. Any questions? Okay, so this was for general Riemannian manifolds, and so now we want to look at the Simpson theorem in the case where X is Kaehler. Okay, so I'm going to give a proof of this, which is basically due to Simpson, and it's kind of a Higgs bundle proof. Okay, so the Simpson theorem holds in much more generality than we're talking about here, but in the particular case where the target is a symmetric space, then you can give a Higgs bundle proof, and that's what I'd like to do now. So let me start by just generally setting up the general formalism here. So let's start again. So given a Higgs bundle, and a Hermitian metric, then I can write, so then let, define a couple operators here. So so I have a, so dA is the Chern connection. Of with respect to the Hermitian metric, okay? And then I'm going to define two operators, namely I'll take the d bar operator of the bundle, and then I'll add p, and then I'll do the opposite here. Okay? So note that this is kind of mixing terms. So this is not of type, it's not pure of type 0, 1. It's mixing the 1, 0 part of the Higgs field and the d bar operator. Okay? So the connection lambda is dA plus phi star, and so this is d prime plus d double. Okay, so we decompose the flat connection in this way. Okay. So to say that we have a Higgs bundle, that if I look at the following tensor, which I'll call G delta, which is D double prime squared. So what happens when I take this squared? I get this squared, I get D bar of phi, and I get phi squared. Okay? So this is the 0, 2 part of the curvature of A. This is D bar A of phi, and this is phi, reg phi, which is also 1/2 of phi bracket phi. Okay? So to say that we have a Higgs bundle means that, first of all, the D-bar operator is integrable, so this part is 0. Phi is holomorphic, this part is 0, and this is the extra condition that one added in the definition of the Higgs bundle, so this part is 0. So G is 0. So this tensor G is 0 in the Higgs bundle case. And what we're trying to achieve in the Hitchin-Simpson correspondence is we're trying to choose the metric so that the curvature of F is 0. So this is FA plus 5 pi star. And we would like to show that this is 0. Okay? What we know is under the assumption if E is polystable plus the Chern class condition, then we know that lambda of FA is 0. E is polystable plus the Chern connection. We know that F is 0. So that's one direction of the Hitchin-Simpson correspondence. So now, what is in the other direction? So conversely, given a flat connection, plus a metric. So flat connection, say lambda, sorry. So then, as I said before, we can write this as dA plus psi. And calling phi the 1,0 part of psi, I can write this as dA plus phi star. Okay? And then I can define the G as before. Okay? So it's a flat connection, so I already know that the curvature is 0. F nabla is 0. And we want G delta to be 0. Because that will say that it comes from the Higgs bundle. So if this is 0, again, this is enough to show that in this decomposition, this is the decomposition of a Higgs bundle, right? Because then all the conditions are satisfied. The D-bar operator of A defines an integrable structure, defines a holomorphic bundle. E is holomorphic with respect to that, and it satisfies this. Okay, so we would like to show this. Okay. Now, Corlet's theorem, that we just proved, implies that that lambda G is 0. Let me just explain that for a second. So here, so the harmonicity I should say for the harmonic metric, right? So if I take a flat connection that's semi-simple, I know that I have a harmonic metric, and I claim that it implies this condition. And why is that? Well, the harmonic metric condition says that dA star of psi is 0. And we already know from flatness that dA of psi is 0. So this is so this implies that dA of phi is 0 just by decomposing in terms of types, and dA bar of phi plus dA bar of phi is 0. Just by decomposing this psi in terms of phi plus phi star, and then decomposing the d bar and d del operators in terms of types. And then what does this condition say? So here I have to use the Kaehler identities. And so by the Kaehler identities, I know that that dA star equals 0 implies that that lambda del A minus del A phi star is 0. Okay, so now taking lambda this, of course we can take lambda this equation here, and now we get what we want. So this implies the two of these together imply that lambda at b bar of A is 0. And so the only thing here that survives, of course, in contraction with the Kaehler form is the 1, 1 part. And so that's the one that we had to check. So, so Corlet's theorem and the harmonicity, the harmonic metric, only tell us that lambda G nabla is 0. What we really want to prove is that G lambda nabla is 0. Okay? And so this is sort of a reformulation in some sense in the Higgs bundle language of the Simpson theorem. And so I think I've run out of time for today, and so maybe I'll do this tomorrow. So tomorrow we want to show that in the case of in this case where in this case actually G nabla is 0. Okay, and so that will be the completion of the proof, because then we know that a flat connection, a semi-simple flat connection, then always comes from a Higgs bundle in this form. All right, so I'll stop there. So why is this 0? In the case of a Higgs bundle, so a Higgs bundle is a holomorphic bundle plus phi, which is a holomorphic section of the tangent bundle tends to be endomorphism bundle. So it's holomorphically restricted. So the d bar operator, so when I write the connection here, dA, the Chern connection, by definition, the d bar operator here is the holomorphic structure coming from E. So that's an integrable holomorphic structure. So that means the d bar squared is 0. Okay, so that's the 0, 2 part of the curvature there. So this is d bar squared. And for a holomorphic bundle, that's always 0. And then phi is holomorphic, and so that's the condition that this is 0. And then, unlike on Riemann surfaces, we have another condition to throw in, namely this, and this is part of the definition of the Higgs bundle as well, is that the bracket of phi with itself is 0. So it's very nice that that's all packaged in this one test.